Welcome to week 2. You'll tackle a new method for classification called naive Bayes. This is another method that's really useful because it's easy to train and provides a quick baseline for your task. With the upcoming exercises, you'll get more practice handling text, loading in data, and doing inference. You'll become familiar with techniques such as Laplacian smoothing and log likelihood analysis. Let's dive into the details.
Okay, here we go. This video will give you an overview of Bayes' rule and go over some probability. Don't worry if your math is a little bit rusty. We'll go through this together, step by step. Probability is fundamental to many applications in NLP, and you will see how you can use it to help classify whether a tweet is positive or negative. So let's get started.
To start, we are going to first review what probabilities and conditional probabilities are, how they operate, and how they can be expressed mathematically. Then, I'll go over how to derive Bayes' rule from the definition of conditional probabilities. Bayes' rule is applied in many different fields, ranging from medicine to education, and is used extensively in NLP. Once you understand the theory behind Bayes' rule, you can use it to perform sentiment analysis on tweets, which will be this week's assignment. Then in the next course, you'll implement autocorrect using its basic formulation as well. Imagine you have an extensive corpus of tweets that can be categorized as either positive or negative sentiment, but not both. Within that corpus, the word happy is sometimes being labeled positive and sometimes negative. Let's explore why this situation is occurring. One way to think about probabilities is by counting how frequently events occur. Suppose you define event A as a tweet being labeled positive, then the probability of event A, shown as P of A here, is calculated as the ratio between the count of positive tweets in the corpus divided by the total number of tweets in the corpus. In this example, that number comes out to 13 over 20, or 0.65. You could also express that value as a percentage, 65% positive. It's worth noting that the complementary probability here, which is the probability of the tweet expressing a negative sentiment, is just equal to 1 minus the probability of a positive sentiment. Note that for this to be true, all tweets must be categorized as either positive or negative, but not both. Let's define event B in a similar way by counting tweets containing the word happy. In this case, the total number of tweets containing the word happy, shown here as unhappy, is 4. Here's another way of looking at it. Take a look at the section of the diagram where tweets are labeled positive and also contain the word happy. In the context of this diagram, the probability that a tweet is labeled positive and also contains the word happy is just the ratio of the area of the intersection divided by the area of the entire corpus. In other words, if there were 20 tweets in the corpus, and 3 of them are labeled positive and also contain the word happy, then the associated probability is 3 divided by 20, or 0.15.
You now know how to calculate the probability of an intersection, for you know how to calculate the probability of a word, namely happy, with the probability of being positive. In the next video, we will talk about naive Bayes. Welcome! We will be looking at conditional probabilities to help us understand Bayes' rule. In other words, if I tell you you can guess what the weather is like given that we are in California and it is winter, then you'll have a much better guess than if I just asked you to guess what the weather is like.
In order to derive Bayes' rule, let's first take a look at the conditional probabilities. Now think about what happens if, instead of the entire corpus, you only consider tweets that contain the word happy. This is the same as saying, given that a tweet contains the word happy, with that, you would be considering only the tweets inside the blue circle, where many of the positive tweets are now excluded. In this case, the probability that a tweet is positive, given that it contains the word happy, simply becomes the number of tweets that are positive and also contain the word happy, and we divide that by the number that contain the word happy. As you can see by this calculation, your tweet has a 75% likelihood of being positive if it contains the word happy. You could make the same case for positive tweets. The purple area denotes the probability that a positive tweet contains the word happy. In this case, the probability is 3 over 13, which is 0.231. With all of this discussion of the probability of meeting certain conditions, we are talking about conditional probabilities. Conditional probabilities could be interpreted as the probability of an outcome B, knowing that event A already happened. Or, given that I'm looking at an element from set A, the probability that it also belongs to set B. Here's another way of looking at this with the Venn diagram you saw before. So, using the previous example, the probability of a tweet being positive, given that it has the word happy, is equal to the probability of the intersection between the tweets that are positive and the tweets that have the word happy, divided by the probability of a tweet given from the corpus having the word happy. Let's take a closer look at the equation from the previous slide. You could write a similar equation by simply swapping the position of the two conditions. Now, you have the conditional probability of a tweet containing the word happy, given that it is a positive tweet. Armed with both of these equations, you're now ready to derive Bayes' rule. To combine these equations, note that the intersection represents the same quantity, no matter which way it's written. Knowing that, you can remove it from the equation. With a little algebraic manipulation, you were able to arrive at this equation. This is now an expression of Bayes' rule in the context of the previous sentiment analysis problem. More generally, Bayes' rule states that the probability of x given y is equal to the probability of y given x times the ratio of the probability of x over the probability of y. And that's it. You just arrived at the basic formulation of Bayes' rule. Nicely done. So to wrap up, you just derived Bayes' rule from expressions of conditional probability. Throughout the rest of this course, you'll be using Bayes' rule for various applications in NLP. The main takeaway for now is that Bayes' rule is based on the mathematical formulation of conditional probabilities, and that, with Bayes' rule, you can calculate the probability of x given y if you already know the probability of y given x and the ratio of the probabilities of x and y. So that's great work. I'll see you later.
Congratulations! You now have a good understanding of Bayes' rule. In the next video, you'll see how you can start applying Bayes' rule to a model known as naive Bayes. This will allow you to start building your sentiment analysis classifier using just probabilities. Welcome! Last week, you learned how to classify tweets using logistic regression. This week, we will solve the same problem using a method called the naive Bayes. It's a very good, quick, and dirty baseline for many text classification tasks, and the concepts you learned will be used later throughout the specialization.
Naive Bayes is an example of supervised machine learning and shares many similarities with the logistic regression method you used in the previous assignment. It's called naive because this method makes the assumption that the features you're using for classification are all independent, which, in reality, is rarely the case. As you will see, however, it still works nicely as a simple method for sentiment analysis. So as before, you'll begin with two corpora, one for the positive tweets and one for the negative tweets. You need to extract the vocabulary, or all the different words that appear in your corpus along with their counts. You get the word count for each occurrence of a word in the positive corpus. Then do the same for the negative corpus, just like you did before. Then, you're going to get a total count of all the words in your positive corpus, and do the same again for your negative corpus. That is, you're just summing over the rows of this table. So for positive tweets, there is a total of 13 words, and for negative tweets, a total of 12 words. This is the first new step for naive Bayes, and it's very important, because it allows you to compute the conditional probabilities of each word given the class, as you're about to see. Now divide the frequency of each word in a class by its corresponding sum of words in the class. So for the word I, the conditional probability for the positive class would be 3 over 13. And you store that value in a new table with the corresponding value 0.24. Now for the word I in the negative class, you get 3 over 12. So you store that in your new table with the corresponding value 0.25. Now apply the same procedure for each word in your vocabulary to complete the table of conditional probabilities. One key property of this table is that if you sum over all the probabilities for each class, you'll get 1. Let's investigate this table further to see what these numbers mean. First, note how many words have a nearly identical conditional probability, like I, am, learning, and NLP. The interesting thing here is words that are equally probable don't add anything to the sentiment. In contrast to these neutral words, look at some of these other words like happy, sad, and not. They have a significant difference between probabilities. These are your power words, tending to express one sentiment or the other. These words carry a lot of weight in determining your tweet sentiment. Now let's take a look at because. As you can see, it only appears in the positive corpus, so its conditional probability for the negative class is 0. When this happens, you have no way of comparing between the two corpora, which will become a problem for your calculations. To avoid this, you will smooth your probability function. Say you get a new tweet from one of your friends, and the tweet says, "I'm happy today, I'm learning." And you want to use the table of probabilities to predict the sentiment of the whole tweet. This expression is called the naive Bayes inference condition rule for binary classification. This expression says that you're going to take the product across all of the words in your tweet of the probability for each word in the positive class divided by the probability in the negative class. Let's calculate this product for this tweet. For each word, select its probabilities from the table. So for I, you get a positive probability of 0.2 and a negative probability of 0.2. So the ratio that goes into the product is just 0.2 over 0.2. For am, you also get 0.2 over 0.2. For happy, you get 0.14 over 0.10. For today, you don't find any word in the table, meaning this word is not in your vocabulary, so you won't include any term in this score. For the second occurrence of I, again, you'll have 0.2 over 0.2. For the second occurrence of am, you'll have 0.2 over 0.2. And learning gets 0.10 over 0.10. Now note that all the neutral words in the tweet, like I and am, just cancel out in the expression. And what you end up is with 0.14 over 0.10, which is equal to 1.4. This value is higher than 1, which means that, overall, the words in the tweet are more likely to correspond to a positive sentiment. So you conclude that the tweet is positive. So far, you've created a table to store the conditional probabilities of words in your vocabulary and applied the naive Bayes inference condition rule for binary classification of a tweet. Great. Next, you'll look into some issues with this implementation and how to fix them.
Now you have seen how naive Bayes can be used to classify the sentiments of a tweet. In the next video, we will simplify the calculations before we implement it. Welcome back! Sometimes you try to calculate the probability of a word happening after a word. To do that, you might want to count the number of times those two words showed up one after another divided by the number of times the first word appeared. Now, what if the two words never showed up next to each other in the training corpus? You get a probability of 0, and the probability of an entire sequence might go to 0. Now, how can we fix this problem? Let's take a look.
Let's now dive into Laplacian smoothing, a technique you can use to avoid your probabilities being 0. The expression used to calculate the conditional probability of a word, given the class, is the frequency of the word in the corpus, shown here as freq of word I, class, divided by the number of words in the corpus, or n class. Smoothing the probability function means that you will use a slightly different formula from the original. Note that I've added a 1 in the numerator. This little transformation avoids the probability being 0. However, it adds a new term to all the frequencies that is not correctly normalized by n-class. To account for this, you will add a new term in the denominator, v-class. That is the number of unique words in your vocabulary, to account for that extra term added in the numerator. So now all the probabilities in each column will sum to 1. This process is called Laplacian smoothing. Going back to this example, let's use the formula on it. The first thing you need to calculate is the number of unique words in your vocabulary. In this example, you have 8 unique words. So now, let's calculate the probability for each word in the positive class. For the word I, the positive class, you get 3 plus 1 divided by 13 plus 8, which is 0.19. For the negative class, you have 3 plus 1 divided by 12 plus 8, which is 0.2. And then so on for the rest of the table. The numbers shown here have been rounded, but using this method, the sum of probabilities in your table will still be 1. Note that the word because no longer has a probability of 0. Great! That's Laplacian smoothing. Now you know why you have to use Laplacian smoothing, so your probabilities don't end up being 0. That's very cool.
You learned about Laplacian smoothing, and now understand why it is important to use smoothing. In the next video, you will learn about the log likelihood. In this video, I will introduce you to log likelihoods. These are just logarithms of the probabilities we're calculating from the last video. But they are way more convenient to work with, and they appear throughout deep learning and NLP.
Okay, so let's go back to the table you saw previously that contains the conditional probabilities of each word, for positive or negative sentiment. Words can have many shades of emotional meaning, but for the purpose of sentiment classification, they're simplified into 3 categories: neutral, positive, and negative. All can be identified by using their conditional probabilities. These categories can be numerically estimated just by dividing the corresponding conditional probabilities of this table. Now, let's see how this ratio looks for the words in your vocabulary. So the ratio for the word I is 0.2 divided by 0.2, or 1. The ratio for the word am is again 1. The ratio for the word happy is 0.14 divided by 0.1, or 1.4. Do the same for because, learning, and NLP. The ratio is 1. And for sad and not, the ratio is 0.1 divided by 0.15, or 0.6. Again, neutral words have a ratio near 1. Positive words have a ratio larger than 1. The larger the ratio, the more positive the word's going to be. On the other hand, negative words have a ratio smaller than 1. The smaller the value, the more negative the word. In this week's assignment, you'll implement a function that filters words depending on their positivity or negativity. You'll find the expression shown here to be very helpful with that. These ratios are essential in naive Bayes for binary classification. I'll illustrate why using an example you've seen before. Recall earlier, where you used the formula to categorize a tweet as positive if the product of the corresponding ratios of every word appears in the tweet is bigger than 1. And we said it was negative if it was less than 1. This is called the likelihood. If you were to take a ratio between the positive and negative tweets, you'd have what's called the prior ratio. I haven't mentioned it till now, because in this small example, you had exactly the same number of positive and negative tweets, making the ratio 1. In this week's assignment, you'll have a balanced data set, so you'll be working with a ratio of 1. In the future, though, when you're building your own application, remember that this term becomes important for unbalanced data sets. With the addition of the prior ratio, you now have the full naive Bayes formula for binary classification, a simple, fast, and powerful method that you can use to establish a baseline quickly. Now it's a good time to mention some other important considerations for your implementation of naive Bayes. Sentiment probability calculation requires multiplication of many numbers with values between 0 and 1. Carrying out such multiplications on a computer runs the risk of numerical underflow. When the number returned is so small, it can't be stored on your device. Luckily, there's a mathematical trick to solve this. It involves using a property of logarithms. Recall that the formula you're using to calculate a score for naive Bayes is the prior multiplied by the likelihood. The trick is to use a log of the score instead of the raw score. This allows you to write the previous expression as the sum of the log prior and the log likelihood, which is a sum of the logarithms of the conditional probability ratio of all unique words in your corpus. Let's use this method to classify the tweet. I'm happy because I'm learning. Remember how you used the naive Bayes inference condition earlier to get the sentiment score for your tweet. Now, you're going to do something very similar to get the log of your score. What you'll need to calculate the log of the score is called the lambda. This is the log of the ratio of the probability that your word is positive, and you divide that by the probability that the word is negative. Now let's calculate lambda for every word in our vocabulary. So for the word I, you get the logarithm of 0.05 divided by 0.05, or the logarithm of 1, which is equal to 0. Remember, the tweet will be labeled positive if the product is larger than 1. By this logic, I would be classified as neutral at 0. For am, you take the log of 0.04 over 0.04, which again is equal to 0. So you enter 0 in the table. For happy, you get a lambda of 2.2, which is greater than 0, indicating a positive sentiment. From here on out, you can calculate the log score of the entire corpus just by summing out the lambdas. You're almost done with the log likelihood. Let's stop here and take a quick look back at what you did so far. Words are often emotionally ambiguous, but you can simplify them into 3 categories, and then measure exactly where they fall within those categories for binary classification. You do so by dividing the conditional probabilities of the words in each category. This ratio can be expressed as a logarithm as well, called lambda, and you can use that to reduce the risk of numerical underflow.
In this video, you learned about the ratio of positive words to negative words. So the higher the ratio is, the more positive the word is going to be. As the number of words we are using gets larger and larger, then we are very likely to get a product that is very close to 0. Hence, we end up taking the log of that ratio. We will continue from the previous video and show you how to do inference. Given your Lambda dictionary, the task is pretty straightforward.
You have done most of the work to arrive at your log likelihood already. Now let's wrap up. Now you can calculate the log likelihood of the tweet as the sum of the lambdas from each word in the tweet. So for word I, you add 0. For am, you add 0. For word happy, you add 2.2. For words because, I, and am, you add 0. And for word learning, you add 1.1. This sum is 3.3, and this value is higher than 0. Remember how previously you saw that the tweet was positive if the product was bigger than 1. With the log of 1 equal to 0, the positive values indicate that the tweet is positive. A value less than 0 would indicate that the tweet is negative. The log likelihood for this tweet is 3.3, and since 3.3 is bigger than 0, the tweet is positive. Notice that this score is based entirely on the words happy and learning, both of which carry a positive sentiment. All the other words were neutral and didn't contribute to the score. See how much influence the power words have. Let's do a quick recap. You used your new skills to predict the sentiment of a tweet by summing all the lambdas for each word that appeared in the tweet. This score is called the log likelihood. For the log likelihood, the decision threshold is 0 instead of 1. Positive tweets will have a positive log likelihood above 0, and negative tweets will have a negative log likelihood below 0. Well done!
Congratulations! Now that you have a good understanding of how to compute the log likelihood and how to do inference, I will proceed to show you how to train a naive Bayes model. This week, I'll show you how to train the naive Bayes classifier. In this context, we train in something different than in logistic regression or deep learning. There is no gradient descent. We're just counting frequencies of words in a corpus.
You'll now be creating, step by step, a naive Bayes model for sentiment analysis using a corpus of tweets that you've already collected. That's awesome! The first step for any supervised machine learning project is to gather the data to train and test your model. For sentiment analysis of tweets, this step involves getting a corpus of tweets and dividing it into two groups, positive and negative tweets. The next step is fundamental to your model's success. The preprocessing step, as described in the previous module, consists of 5 smaller steps. 1. Lowercase the text. 2. Remove punctuation, URLs, and handles. 3. Remove stop words. 4. Stemming or reducing words to their common stem. And 5. Finally, tokenizing or splitting your document into single words or tokens. For the assignments in this week, it will be relatively straightforward to implement this processing pipeline. But in the real world, you might find the gathering and processing of text takes up a big chunk of your project's hours. Once you have a clean corpus of processed tweets, you'll start by computing the vocabulary for each word in class, like you did in the previous week. This process will produce a table like the one shown here. You can compute the sum of words and class in each corpus in this same step. From this table of frequencies, you get the conditional probability, or probability of word given class, by using the Laplacian smoothing formula. See how the number of unique words in V class is equal to 6. You only account for the words in the table, not the total number of words in the original corpus. This produces a table of conditional probabilities for each word in each class. This table only contains values greater than 0. For the fourth step, you'll get the lambda score for each word, which is the log of the ratio of your conditional probabilities. The fifth step is the estimation of the log prior. To do this, you'll need to count the number of positive and negative tweets, and then the log prior is the log of the ratio of the number of positive tweets over the number of negative tweets. In the upcoming assignment, you'll be working with a balanced dataset, so the log prior is equal to 0. But for unbalanced datasets, this term will become important. In summary, training a naive Bayes model can be divided into 6 logical steps. You get or annotate a dataset with positive and negative tweets. Typically, it's better if your tweets match the same context that you want to use in the final model. Then you process the raw text to get a corpus of clean, standardized tokens. You compute the dictionary of frequencies for each word in class, then compute the conditional probabilities of each word using the Laplacian smoothing formula. You compute the lambda factor for each word, and finally, you estimate the log prior of the model, or how likely it is to see a positive tweet in your account. Wow, that was quite a lot.
Now, you have seen how to build the probability table needed to apply naive Bayes. The next exciting thing we'll do is to classify your sentences. This part will be fun, as you will apply the naive Bayes classifier on real test examples. It is similar to what you did in the first video of the week, but we'll cover some special corner cases.
Once you have trained your model, the next step is to test it. And you do so by taking the conditional probabilities you just derived, and you use them to predict the sentiment of new, unseen tweets. After that, you'll evaluate your model performance, and you'll do so just like how you did it in the last week. You use your test set of annotated tweets. With the calculations you've done already, you have a table with the lambda score for each unique word in your vocabulary. And with your estimation of the log prior, you can predict sentiment on a new tweet. This new tweet says, "I passed the NLP interview." You can use your model to predict if this is a positive or negative tweet. So before anything else, you must pre-process this text, removing the punctuation, stemming the words, and tokenizing to produce a vector of words like this one. Now, you look up each word from the vector in your log likelihood table. If the word is found, such as I, pass, the, and NLP, you sum over all the corresponding lambda terms. The values that don't show up in the table of lambdas, like interview, are considered neutral and don't contribute anything to the score. Your model can only give a score for words it's seen before. Now you add the log prior to account for the balance or imbalance of the classes in the dataset. So this score sums up to 0.48. Remember, if this score is bigger than 0, then this tweet has a positive sentiment. So yes, in your model and in real life, passing the NLP interview is a very positive thing. You just predicted the sentiment of a new tweet, and that's awesome. It's time to test the performance of your classifier on unseen data, just like you already did for a different scenario in the previous module. Let's quickly review that process. As applied to naive Bayes, this week's assignment includes a validation set. This data was set aside during training and is composed of a set of raw tweets, so xval, and their corresponding sentiments, yval. You'll have to implement the accuracy function to measure the performance of your trained model, represented by the lambda table and the log prior, using these data. First, compute the score of each entry in xval, like you just did previously. Then, evaluate whether each score is greater than 0. This produces a vector populated with zeros and ones, indicating if the predicted sentiment is negative or positive, respectively, for each tweet in the validation set. With your new predictions vector, you can compute the accuracy of your model over the validation set. To do this part, you will compare your predictions against the true value for each observation from your validation data, yval. If the values are equal and your prediction is correct, you'll get a value of 1, and 0 if incorrect. Once you have compared the values of every prediction with the true labels of your validation set, you can compute the accuracy as the sum of this vector divided by the number of examples in the validation set, just like you did for the logistic regression. Okay, let's revisit everything you just did. To test the performance of your naive Bayes model, you use a validation set to allow you to predict the sentiment score for an unseen tweet using your newly trained model. Then, you compared your predictions with the true labels provided in the validation set to get the percentage of tweets that were correctly predicted by your label. Then, you compared your predictions with the true labels provided in the validation set, and this allowed you to get the percentage of tweets that were correctly predicted by your model. You also saw that words that don't appear in the lambda table are treated as neutral words.
Now you know how to apply the naive Bayes method to test examples. In the coding exercise at the end of the week, you will use it to classify tweets. Next, I'll show you other things it can do. Earlier in the week, you used a naive Bayes method to classify tweets, but that can be used to do a number of things like identify who's an author of a text. I'll give you a few ideas of what those things may be.
When you use naive Bayes to predict the sentiments of a tweet, what you're actually doing is estimating the probability for each class by using the joint probability of the words in classes. The naive Bayes formula is just the ratio between these two probabilities, the product of the priors and the likelihoods. You can use this ratio between conditional probabilities for much more than sentiment analysis. For one, you could do author identification. If you had two large corpora, each written by different authors, you could train a model to recognize whether a new document was written by one or the other. Or if you had some works by Shakespeare and some works by Hemingway, you could calculate the lambda for each word to predict how likely a new word is to be used by Shakespeare or alternatively by Hemingway. This method also allows you to determine author identity. Another common use is spam filtering. Using information taken from the sender, subject, and content, you could decide whether an email is spam or not. One of the earliest uses of naive Bayes was filtering between relevant and irrelevant documents in a database. Given a set of keywords in a query, in this case, you only needed to calculate the likelihood of the documents given the query. You can't know beforehand what irrelevant or irrelevant document looks like. So you can compute the likelihood for each document in your dataset and then sort the documents based on its likelihoods. You can choose to keep the first M results, or the ones that have a likelihood larger than a certain threshold. Finally, you can also use naive Bayes for word disambiguation, which is to say, breaking down words for contextual clarity. Consider that you have only two possible interpretations of a given word within a text. Let's say you don't know if the word bank in your reading is referring to the bank of a river or to a financial institution. To disambiguate your word, calculate the score of the document, given that it refers to each one of the possible meanings. In this case, if the text refers to the concept of river instead of the concept of money, then the score will be bigger than 1. That's cool, right? In summary, Bayes' rule and its naive approximation has a wide range of applications in sentiment analysis, author identification, information retrieval, and word disambiguation. It's a popular method since it's relatively simple to train, use, and interpret. You'll be using the Bayes rule and naive Bayes again in the weeks ahead. Now, you're fully equipped.
As you've seen in this video, naive Bayes can be used for many classification tasks. Next, I'll show you the assumptions that underlie the naive Bayes method. Now I'll go into the assumptions underlying the naive Bayes method. The main one is independence of words in a sentence, and I'll tell you why this can be a big problem when the method is applied.
Naive Bayes is a very simple model because it doesn't require setting any custom parameters. This method is referred to as naive because of the assumptions it makes about the data. The first assumption is independence between the predictors or features associated with each class, and the second has to do with your validation set. Let's explore each of these assumptions and how they could affect your results. To illustrate what independence between features looks like, let's look at the following sentence. It is sunny and hot in the Sahara Desert. Naive Bayes assumes that the words in a piece of text are independent of one another. But as you can see, this typically isn't the case. The words sunny and hot often appear together as they do in this example. Taken together, they might also be related to the thing they're describing, like a beach or a desert. So the words in a sentence are not always necessarily independent of one another. But naive Bayes assumes that they are. This could lead you to under or overestimate the conditional probabilities of individual words. When using naive Bayes, for example, if your task was to complete the sentence, "It's always cold and snowy in blank," naive Bayes might assign equal probability to the words spring, summer, fall, and winter. Even though from the context you can see that winter should be the most likely candidate. In the next courses of this specialization, you will be introduced to some more sophisticated methods that deal with this. Another issue with naive Bayes is that it relies on the distribution of the training datasets. A good dataset will contain the same proportion of positive and negative tweets as a random sample would. However, most of the available annotated corpora are artificially balanced, just like the dataset you'll use for the assignment. In a real tweet stream, positive tweets tend to occur more often than their negative counterparts. One reason for this is that negative tweets might contain content that is banned by the platform or muted by the user, such as inappropriate or offensive vocabulary. Assuming that reality behaves as your training corpus, this could result in a very optimistic or very pessimistic model. There's a lot more on this in the last video of this module, which analyzes the sources of errors in naive Bayes. Let's do a quick recap of all this new information. The assumption of independence in naive Bayes is very difficult to guarantee, but despite that, the model works pretty well in certain situations. And for the assignments in this module, the relative frequency of positive and negative tweets in your training dataset needs to be balanced in order to deliver an accurate result.
Now you understand the assumptions that underlie the naive Bayes method. What if it fails to perform well for some sentence? In the next video, I'll show you what to do in such cases. No matter what NLP method you use, You will one day find yourself faced with an error. For example, a misclassified sentence. In this video, I'll show you how to analyze such errors.
Let us consider some possible errors in the model prediction that can be caused by these issues. 1. Semantic meaning lost in the pre-processing step. 2. How word order affects the meaning of a sentence. And 3. Some quirks of language that come naturally to humans, but confuse naive Bayes models. So let's start. One of your main considerations when analyzing errors in NLP systems is what the processed version of the text actually looks like. Let's look at this tweet. My beloved grandmother, with some punctuation indicating a sad face. The sad face punctuation in this case is very important to the sentiment of the tweet, because it tells you what's happening. But if you're removing punctuation, then the processed tweet will leave behind only beloved grandmother, which looks like a very positive tweet. My beloved grandmother, ! Would be a very different sentiment. So remember, always check what the actual text looks like. It's not just about punctuation either. Check out this tweet. This is not good because your attitude is not even close to being nice. If you remove neutral words like not and this, what you're left with is the following: good, attitude, close, nice. From this set of words, any classifier will infer that this is something very positive. I'll talk later on about handling not and word orders. But remember, double check what your processed text looks like to make sure your model will be able to get an accurate read. The input pipeline isn't the only potential source of trouble. Look at these tweets. I'm happy because I did not go. This is a purely positive tweet. I'm not happy because I did not go with a negative sentiment. In this case, the not is important to the sentiment, but gets missed by your naive Bayes classifier, so word order can be as important as spelling. There are many other factors to consider as well, and you will see more and more ways to build systems that handle them in the weeks to come. Another problem of naive Bayes is something called an adversarial attack. The term adversarial attack describes some common language phenomena like sarcasm, irony, and euphemism. Humans pick these up quickly, but machines are terrible at it. This tweet: this is a ridiculously powerful movie. The plot was gripping, and I cried right through until the ending, contains a somewhat positive movie review, but pre-processing might suggest otherwise. If you pre-processed this tweet, you'd get a list of mostly negative words, but as you can see, they were actually used to describe a movie that the author enjoyed. If you use naive Bayes on this list of words, it would end up giving a very negative score regardless.
Now you know how to apply the naive Bayes method to text classification. It makes the independence assumption, which can lead to errors, but you know how to analyze them. It's still a very powerful baseline. As you know, it relies on word frequency counts. Next week, we can learn how to use word vectors that can give us better results.
Congratulations on completing this week's materials! You learned about Bayes' rule and conditional probability. You computed the likelihood of a word being associated with a particular sentiment by computing the probability of that word being associated with positive sentiment, and then dividing it by the probability of that word being associated with a negative sentiment. You also learned how to do error analysis, which is an important tool that allows you to debug your model if it's not working. Many of the skills you've learned here can easily be transferred when deploying other models in the specialization. Next, you'll apply these skills in this week's programming assignment, and after that, we'll be looking at cosine similarity and principal component analysis. Good luck in the programming assignment!
Good luck!